Okay, this is Module 5, Velocity Analysis using Jacobian. In this module, we're going to learn how to calculate the velocity of robotic system based on the configuration of the robotic device using Jacobian matrix. Also, after getting Jacobian matrix, we can obtain the coefficients of individual joints by inversing the Jacobian matrix and doing some calculation. So let's get started. So the first thing we want to know about is how do we analyze velocity. If you have taken dynamics already, then you must know that in order to find out what is my uh, kinematic in 3D dimension, we need to have several information. The first one is position, of course. And the other one, we also need to know angular velocity. The configuration is pretty straightforward. If we projected everything onto two-dimensional plane, so we got two-dimensional plane, x and y. And we have a bar, which is rigid body. So when this one starts to rotate at omega, the angular velocity, then we can find out the velocity, linear velocity at this point is going to be in this direction. And if we know the distance over here is r, velocity is going to be r omega, must be perpendicular to this specific linkage. If we represent everything using vector representation, then this is the format we're going to have. We got a vector of angular velocity, then it's going to be theta dot multiplied by k. K over here is a unit vector along the axis. Keep in mind when we are dealing with rotation, the rotation must be perpendicular to the velocity. So if we are doing two-dimensional case, then the angular velocity followed by the right-hand rule is always point out the paper, which is going to be positive. If it's pointing in this direction, then it is going to be negative. If you point out, then it's going to be counterclockwise. If you're pointing in, that is going to be clockwise. That is a right-hand rule we learn in dynamics. But when we try to find out the linear velocity or translation speed, this formula is something we're going to use. It's still vector representation, but this time it's going to be in 3 dimensions. What I mean is, when I get V, it must be I, J, and K as the first row. For the second row, since we say it's omega cross product R, then it must be omega X, omega Y, omega Z, Rx, Ry, and Rz. Then we get the information. This part is going to be explained in the later part of the class. But over here, what we're trying to do is to find out the formula that is going to give us the velocity in 3 dimensions. That is something we have already learned in dynamics. Before we move on to Jacobian, let's take a look what the traditional way of getting velocity. So this is a very typical problem you might encounter in dynamics. We got the crank AB rotates about with a constant angular velocity of 5 radians per second. We want to determine the velocity of block C and the angular velocity of link BC at this instant when theta equals to 30 degrees. Theta is over here. And we got some kind of configuration A, B, and C. In this specific problem, C, the block C, needs to be moved horizontally. It cannot move vertically, which means the direction of the movement has been restricted. That will give us a lot of benefit of figuring out how the angular velocity of bar BC is going to look like. Before we move on, before we actually start to solve everything, we want to define what are given. We are given theta equals to 30 degrees. At this moment, our omega AB is 5 radians per second. In this case, it is positive. And we want to find out two things. what is my angular velocity of BC, and the other one is what is my velocity of C at this instant. Just like what I said, this specific block over here has restricted moving direction. So only after you're doing the calculation, you can only have the velocity along x-axis. If you come up with some answer, you got velocity along y-axis, then it is going to be wrong. Before we move on, we need to figure out the direction of bar BC at this instant. So let's do a little bit geometry relationship calculation. Okay, so we got this bar over here, 0.6 meter. This one over here is 30 degrees. And we're going to figure out what we have over here. So since this one is 30 degrees, the height of this specific triangle is going to be 0.6 sine 30 degrees, which means this one over here is 0.3 meter. And this one over here is going to be 0.6 cosine 30 degrees, which is going to give us 0.5196 meter. Or you can say this one is 0.52. Okay, and we are given that this bar of this distance over here is 0.15 meter, which means it should be pretty straightforward to figure out what's going on. Since we know the length over here is 0.3 meter, which is given over here, and we know this part is 0.15, so this part must be 0.15, which yield the angle over here is 30 degrees as well. So based on this configuration, we have figured out all the geometry information that we require for doing calculation. So we can start to do our calculation. So start to solve. We know my omega AB is 5k radians per second. Then I can come up with my BB, that is going to be VA plus omega AB cross product RB over A. This specific setup over here is you want to find the relative velocity at point B based on the observation at A. This is important when you are dealing with the problem in dynamics. If you fail to identify what's going on in your system, then it would be very likely you're going to get the wrong answer. So VA, obviously, this point is a fixed one. So we do not have any velocity over here. So this one is going to be 0 plus 5k cross product. Since we have all the geometry information on the other side, we can just plug in. That is going to be a 0.52 I plus 0.3 J. Okay, so with those information, it is straightforward for us to figure out the velocity is actually negative 1.5 J plus 2.6. Oh, I'm sorry, this one should be I. This one is J. Okay, so if you forget, you can use this method A, B, C, D, E, F. You go through this direction, then minus this direction. This should be in your calculus textbook or other basic math you learn in freshman or sophomore. This part is pretty straightforward. So once we get this one down, then the next thing is we need to figure out what's going on for VC. So VC is going to be the same. It's going to be VB plus omega BC cross product RC over B. Okay, so this part over here, since we have obtained the velocity at point B, so we can just plug the number into this equation. Omega BC is something we need to find out, but obviously it should be rotated about a specific axis, which means the direction of omega BC must be K. The other thing we need to know is what is my x component and y component of RBC based on the observation at point B. So in that case, I'm attaching an, let me do something over here. So I need to attach the coordinate over here. This is x and y. I'm not dealing with anything about robotics calculations for now. It has nothing to do with module 2, 3, or 4. This one is just come up with the angular velocity based on the regular xy components. So if I attach xy over here, then RC over B must be positive 0.26, and the x is going to be negative 0.15. So we're going to use this piece of information to come up with our calculation. Let's move on to the next page. Let me change my color back. So from the previous page, we know that VC is going to be VB plus omega BC cross product RC over B. And VB is negative 1.5 I plus 2.6 J. That is from the calculated result in the previous page. And this time I have omega BC, again K, cross product 0.26 I minus 0.15 J. Okay, so that's a basic setup of everything. Then we can come up with the answer like negative 0.15 I plus 2.6 J. Those two remains the same. The next one is going to be 0.26 omega BC J minus 0.15 omega BC I. So group them together. I got should be plus. This is I component. Okay, so I got two parts. Can we find out the answer of omega BC? Of course, because we know at point C it's a cylinder and it's only moved along horizontal axis, which means this one over here must equals to 0, and this one over here is the velocity that we're going to use. So clearly 2.6 plus 0.26 omega BC equals to 0, which yield omega BC equals to negative 10 radians per second. This is one of the answer. When we have this specific number, then VC is going to be negative 1.5 plus 0.15 multiplied by negative 10. Of course, I. Then you're going to get this answer is going to be negative 3 I meter per second. This one over here is going to be my answer as well. So when you have those kind of a configuration and you have good skill, you learn from dynamics, this should not be a problem. However, we all know that if it's a two-part linkage, it's still easy for us to do the calculation. But if you need to find out the answer when the mechanism is like 4, 5, 6, 7 bars, then it can be a little bit difficult. In particular, if you need to rotate everything in three-dimensional space, then the calculation can be very, very tedious. So that is something we're going to use. We're going to talk about using Jacobian to help us to simplify the calculation